Welcome to Math Tutorials. In this video, we are solving every question of exercise 3.2 of Chapter 3, Matrices, from the NCERT Mathematics textbook for Class 12, Part 1. Exercise 3.2 is the big one, 22 questions on matrix operations. Addition, scalar multiples, matrix multiplication, matrix equations, 2 word problems, and 2 order of matrix questions. Here is the list. Let's get started. Question 1. 3 2 by 2 matrices, and 5 things to compute with them. 2 sums, a scalar combination and both products, in both orders. A plus b, add entry by entry. A minus b, subtract entry by entry, note 3 minus 2 is 5. 3 a scales every entry of a by 3, then subtract c. A b, rows of a against columns of b. The top left entry, for instance, is 2 times 1 plus 4 times minus 2, which is minus 6. And ba, the other order. 2 plus 9 is 11, 4 plus 6 is 10, minus 4 plus 15 is 11, minus 8 plus 10 is 2. A completely different matrix. Question 2. 4 sums, algebraic, numeric, and trigonometric. Addition is always entry by entry. Watch Part 4 collapse using the Pythagorean identity. Part 1, the b's cancel in the bottom left. Part 2, each entry completes a perfect square. Part 3, write every entry sum, then evaluate. Part 4, every entry is cosine squared plus sine squared, all ones. Question 3. 6 multiplications of every shape, rows against columns throughout. Part 2 is the fun one. A column times a row blows up into a full 3 by 3. Part 1, write each entry as a row times a column. The cross terms cancel, leaving a squared plus b squared on the diagonal. Part 2, each entry of the column multiplies each entry of the row, all 9 products written out. Part 3, every one of the 6 entries written as its 2-term sum, then evaluated. Part 4, all 9 3-term sums written before evaluating. Part 5, the entry sums written, giving a 3 by 3. And Part 6, 4 3-term sums, evaluated to a 2 by 2. Question 4. 2 computations, then a verification of associativity of addition with a subtraction mixed in. Both sides of the verification should land on the same matrix. A plus b entry-wise. B minus c entry-wise. Left side of the check, a plus the difference. Right side, the sum minus c the same matrix, verifying the identity. Question 5. Fractions everywhere, but watch what the scalars 3 and 5 do to them. Matrix A is built from thirds and B from fifths. The scalars 3 and 5 are chosen to clear them. Multiply every entry of a by 3. Each third clears to a whole number. Now every entry of B times 5. The fifths clear to exactly the same whole numbers. Identical matrices subtract to the 0 matrix, entry by entry. Question 6. Push each scalar inside its matrix, add, and let the Pythagorean identity do the rest. We push each scalar inside its matrix, add, and simplify with the Pythagorean identity. Distribute the scalars into every entry. The off-diagonal terms cancel, the diagonals sum to 1, the identity matrix. Question 7. Simultaneous equations, but the unknowns are whole matrices. The algebra works exactly like ordinary elimination. Part 2 needs a genuine elimination step. Part 1, adding the equations gives 2x, subtracting gives 2y. Part 2, scale the first equation by 3 and the second by 2, subtract, and 6x cancels, leaving 5y, every entry shown. Divide by 5 for y. Then 2x is the first right side minus 3y, written entry by entry, and halved. Question 8, a quick rearrangement. Y is known, so we simply isolate x from the equation. Move y across. 2x is the right side minus y. Have every entry. Question 9, scale add then match entries. The result matrix on the right pins both unknowns down. The left side combines to 2 plus y, 6, 1, 2x plus 2. Top left gives y equals 3. Bottom right gives 2x plus 2 equals 8, so x equals 3. Question 10. Same recipe at full scale, 4 unknowns from 4 entries. Everything on the left must equal 3 times the last matrix. Expand both sides. Match the entries one by one. X is 3, Z is 9, Y is 6, T is 6. Question 11. A vector equation hiding 2 ordinary equations. X scales one column, Y scales the other, and together they must hit the target column. Reading off the 2 rows, 2x minus y is 10, and 3x plus y is 5. Adding kills y. 5x equals 15, so x is 3, and then y is 5 minus 9 minus 4. Question 12. Unknowns on both sides this time. Each entry becomes a small equation to untangle. The entries mix the unknowns across both sides, so each position gives its own little equation. Top left, 3x equals x plus 4, so x is 2. Top right, 3y equals 6 plus x plus y. With x known, 2y is 8, y is 4. Bottom right, 3w equals 2w plus 3, so w is 3. Bottom left, 3z equals z plus w minus 1, giving 2z equals 2, z is 1. Question 13, the rotation matrix. Multiplying 2 of them should rotate by the combined angle. Multiplying f of x by f of y should produce f of x plus y. Rotation angles add. Multiply the 2 matrices. The top left entry is cos x cos y minus sin x sin y. The neighboring entry is minus the sum sin x cos y plus cos x sin y, exactly minus sin of x plus y. The third row and column pass through untouched, so the product is exactly the rotation by x plus y. Question 14. Concrete proof that matrix multiplication does not commute. We compute both orders and compare. We compute each product in both orders and show they differ. Part 1, first order. Each entry written as its row times column sum. The reversed order, every entry written, a different matrix, not equal. Part 2, the first order with all 9 sums written. And the reversed order, all sums written, visibly different from the first entry onward. Question 15. A matrix polynomial, square a scale a, add the identity, then combine. A squared, all 9 row times column sums written, then evaluated. Then 5 and 6i. Combine entry by entry, every one of the 9 sums written before evaluating. Question 16. A cubic identity, we need a squared and a cubed, then the combination should vanish entirely. A squared, all 9 sums written. Multiply once more for a cubed, again every sum written. Now the full combination, entry by entry, all 9 sums on screen. All 9 entries evaluate to 0, so the combination is the 0 matrix. Identity proved. Question 17. One unknown scalar k, pinned down by a matrix equation. We square a, write out k a minus 2i, and match entries. A squared with each of the 4 entries written as its sum. Write out k a minus 2i and compare the top right entries. Minus 2 k equals minus 2, so k is 1. Check the remaining entries with k equal to 1, all 4 match. Question 18, the hardest identity here. Write t for tan of alpha by 2 and use the t formulas for sine and cosine. Both sides are 2 by 2 matrices in t. We multiply out the right side and watch it become I plus a, with t as shorthand. Cosine alpha is 1 minus t squared over 1 plus t squared, and sine alpha is 2t over 1 plus t squared. The right side is I minus a times the rotation. Multiply. The top left entry is cosine alpha plus t sine alpha. Substitute, and it collapses to 1. The top right entry works out to minus sine alpha plus t cosine alpha. Substituting gives exactly minus t. By symmetry, the bottom row gives t and 1, assembling exactly I plus a. Identity proved. Question 19, a word problem. Let x go into the 5% bond and the rest into the 7% bond. The interest condition becomes a 1 by 2 times 2 by 1 matrix product. Set up the product. The amounts row times the rates column equals the interest. Case A, 0.05x plus 0.07 times the rest equals 1,800, which solves to x equals 15,000. So 15,000 in each bond. Case B, the same equation with 2,000 gives x equals 5,000. That is 5,000 at 5% and 25,000 at 7%. Question 20. Counts times prices, a natural row times column product. Prices are 80, 60, and 40 rupees. A row of counts times a column of prices gives the total. Convert dozens to books. 120, 96, and 120 copies. Multiply by the price column. The total is 20, 160 rupees. Question 21. Multiplication needs inner orders to match. Addition needs the results to be the same shape. The 5 matrices have orders 2 by n, 3 by k, 2 by p, n by 3, and p by k. P by k times 3 by k needs k equal to 3, and then the product is p by k. Wy is n by 3 times 3 by k, defined, with shape n by k. For the sum, p must equal n. The last question. X is 2 by n and z is 2 by p, and n equals p. Scalar multiples keep each shape, and with n equal to p both are 2 by n, so the difference is 2. That completes exercise 3.2. That completes all 22 questions of exercise 3.2. In the next video, we will take up exercise 3.3 on the transpose of a matrix. Thank you for watching. If you found this video helpful, do like it, subscribe to math tutorials, and share it with your friends.